everyone. In this video, I want to demonstrate how to estimate pool model in R. So this is my R environment. So I've already set my working directory with the right folder. So I want to open the prepared script for this estimation. I'll go to File, then I'll go to Open File. Then I pick the file, the script, the house script I already wrote. So here's the house script. Then I open. So here's the house script I want to use to carry out the analysis. So the first thing I'm going to do is that I want to import the data set. I can import data set using this line of code. So this is the function I'm going to use to import data set, read.csv. I can use this code to import data set, okay, by just running this. So you can see in this environment here, you will see that the data set has been imported, okay. Another way of importing data set is just to go to File, you go to File, then you click on Import Data Set, then from Text Base, if I click on Text Base here, so that will allow you to be able to pick the data set. So the name of data set is Grunfeld. So here is it. So I click Open. Then I go down. Then I click on Import. You can see data set has been imported. Okay, so you can also import data through that. So let me just cancel this. I've already imported the data set. Now, I can also view the data set after using this line of code to import data set. So I want to go by this code. So if I click on View, I insert the name of data set. So I'm going to see the data set coming up. You can see the data set in panel format. So going back to the house script. So the appropriate package to estimate panel model in R is called PLM package. So I'm going to load that package by using the function library. So I'm running the line of code in line 6 to load the package PLM. So PLM, you can see the package has been loaded. To load the package, I can also come to the package here and look for PLM. Okay, PLM, I can just type it there, PLM. You can see, I'll just tick it. You can see I've been ticked because I've already loaded it. Okay. So now, to estimate pool LS, that's the pool model. So we are going to use, we have two options. Is that we use LM function. LM function, that's LM function that we normally use to estimate our linear regression model. Linear regression model in time series. So this LM function, so I have the variable investment here. Because I'm logging it, I write the log in front of the variable. Then I check value, log value, the value, and I also plus the log of capital, then comma, data equals to the name of the data set. Here, this is the name of the data set, so I put that. So if I run this line of code in line 8, that helps me to estimate pool model. So I've already, yes, I'm able to estimate pool model. To see my result, I'll just run a line of code in 9. That is summary function. I'm going to use summary function then. I put PLS there. That is the name I use to store my estimation. And I'll have my result. You can see after hitting the bar, the result will come up. You can see now that I have my result now coming up. I have my result. You can see I have my results coming up now. Here, I have the value of the intercept. I have the value of the log of value. I have log of capital. You can see the estimates for this. You can see the statistics. You have the p-value. You can see we have the p-value. We have the p-value here. P-value. You can see we have the p-value here. Okay. So you see that since our dependent variable is the log of investment, so we are to interpret the coefficient of the log of value here. So this simply implies that 1% increase in market value, in firm's market value, will result in about 0.77% increase in an investment, in a firm's investment. So also for capital, we have if there's a 1% increase in capital stock, that will result in about 0.38% increase in firm's investment. You can see that is interpretation. And all the coefficients are significant. You can see they are significant, even at 1%. Significant. So this line of code in line 10, you must have come across this before, okay? In case you have your p-value in standard form, so you can actually run this line of code before running this summary so that you have your clear result. Since we already have our clear result, so we don't need, since we already have our probability value not in standard form, so we can ignore this, okay? Now, an alternative way of estimating pool model is by using, you can see here, this LM here, this LM function here, so is an half-based function, okay? It's an half-based, so we can use it to estimate our pool OLS, that is pool model. So also, alternatively, we can actually use this function PLM that's available in package, okay? So this PLM, but before we can use PLM function, we have to set our data set as panel, okay? So I'm changing it. I'm going to use p.grumfed. So I'm adding p to indicate that it's panel setting. So I want to use the function panel, that's p data.frame. So I put the name of data set, comma index. So see, I put firms in inverted comma, and I also put here inverted comma. So what firm represent our cross sections, and here represent the time period. Okay, so you can see that's panel setting. So after doing that, let me set my data set as panel. So that will allow me to maybe use this PLM function. Okay, now you can see the structure. I'm using PLM function, so I'm going to have the same here, the same thing, the same formula here. You can see, comma, then data set. So instead of putting Grumfed, I'm going to use p.grumfed. That is the name I use to save my panel setting. Then model equals to pooling. That is pool model, telling how that I'm estimating pool model. If I run this code, it's going to help me to estimate pool model. Then I'll be able to estimate pool model. Let me see the result. If I click on this, I will have the same. You can see you have the same result, okay? Compared to when you have when you use function LM, you can see the same result you are going to have. Okay, this is the estimation. So now the next thing is to carry out diagnosis test. We want to carry out diagnosis test. That's the next thing. Okay, carrying out diagnosis test. Okay, the next thing is that you the first diagnosis test we want to carry out, that is a serial correlation test, and we are going to use the function PBG test. Okay, PBG, that will help us to use Gottfried, or what they call Woodruff test for serial correlation in panel model. So we want to test at order 2. So then you can see for polling model. So now if I run this line of code, I just put model there. I use POLS to sort the result. Then order, meaning that order of 2, I can change it to 3. I can start from 1. So this is a higher order, 2, 3, 4, 5. I can change it. So I want to test at order 2, which is the usual case. So if I run this, so that will give you can see the result here. I just check the p-value. The p-value is less than 0.05. That is the conventional level of significance. So this indicates that the residuals are serially correlated. So this implies that residuals are serially correlated. Okay. Now the next diagnostic I want to carry out, that is a heteroscedasticity test. Heteroscedasticity test. Okay. So in order to do that, we need a package called LM test. LM test. So we are going to load that package. So to load it, I'm going to use the function library, the bracket LM test. Okay. So if I hit the bar, so you can see I'm able to load it. Then let me run it. So I just put BP test function from LM test. Then I put the name of the name I used to test the result. Then I studentize, I set it to F. Okay, that is false. Okay, so then I hit where you can see this helps me to test for heteroscedasticity. You can see that the errors are heteroscedastic. You can see because this is also significant. Okay, so because we have the problem of serial correlation and heteroscedasticity, so we want to use robust covariance matrix estimators. Okay, we want to use robust estimator to estimate our covariance in order to correct our standard error. We want to correct for the impact of serial correlation and heteroscedasticity on our t-test, and that is standard error and t-test. Okay, because we have the problem of heteroscedasticity or serial correlation or both. Our standard errors are usually underestimated. So we want to correct that by using robust covariance matrix estimator. So to do that, to correct for serial correlation, okay, so just this one is just for a particular purpose, because we want to, if you, assuming you have a case whereby your model is only suffering from serial correlation, so we are going to use summary, and we had VCOV equals to VCO during heteroscalar HC. So we are going to adjust for that. So by running that, that is going to adjust for our standard error, and automatically t-test will be affected. So let me rerun it. You can see t-test has been affected. We have 3.8619, and we have 6.19, and you can see compared to what we had before. So let's go up. If you go up, you can see here you have 22.196. Okay, and you can see the standard error very small here, but here standard error has been adjusted. Is that standard errors have increased? Standard errors have increased. You can see. So meaning that this has helped us to correct for serial correlation. But because our model is suffering from both serial correlation and heteroscedasticity, so we are going to use this line of code. So we are going to adjust by adding this Arellano method Arellano to it. You can see the structure. So if I run this, okay, so you can see no difference between when I run serial correlation and when I correct for serial correlation alone and heteroscedasticity and serial correlation. You can see